Okay, the microphone should be on, right?
It should already be on.
Yeah,
You're picking it up. So.
it has red light. Is this normal?
Just
That's the battery is actually seems to be.
off to a great start. You know what? Let me just give you the other mic.
Yeah. It used to be green,
Yeah.
Now it's red.
I guess yeah, we left it on because we were testing, and now. Try that out. It should be.
Okay, so that has. Mic on. Then, yeah. So suppose. Say it again. I know. Yes. Yeah. So yeah, I'm muted. Right. Now. Minutes to go to this live stream, right? And okay, yeah. But in about weird ways, lectures hope let the people not working. So you cannot hear me, right?
Yeah, for some reason this one, I don't know, when wasn't always picking it up.
Okay. So hopefully works now. So how can you test it?
Well, we're getting consistent audio off of it now.
Uh huh. You are getting a consistent audio, right? Mm-hmm. Okay. All right, so sound should work now. Hopefully. Okay. Very well. Sound should work. And again, maybe one more minute. We wait for everybody else to join. Start their YouTube feed. Has been sent by email. Yeah. Okay. Um, well, okay, yeah. So once again, I think I'm going to send the people the link because the chat kind of disappears, right? Okay, so I'm sending the link again. Okay. And where is that link? There it is. Not everybody went to. Yeah. Okay, maybe one more minute. Yeah. Well, is it usable? Totally usable. All right. So maybe you don't want to break it, right? Huh. Yeah. Mm-hmm. Right. Yeah. Whew. Okay. I don't think we want to break anything now, right? It's been already almost 10 minutes, right? And I'd better start the lecture now. Right, yeah, okay. All right then. So we are starting. I know it's not perfect, and it probably won't be perfect. This is the first time also. Things are changing day by day, as you know, and we may start meeting in different format at some point. So We apologize for this, but this is absolutely not under our control, obviously. So for now, hopefully you can see and hear me. Once again, you should be on the YouTube stream now, and therefore there is about 10-second delay between the actual lecture and what you see and hear. We'll try to accommodate questions. The way it's going to work is this: you unmute your mic and ask your question. Obviously there will be a 10-second delay. I'll try answering. We'll see how it works. Maybe we'll improve it in some way in the future, but for now we'll have to live with this delay. Then obviously there are obvious questions about exams and grading, and I cannot answer these questions now, but once we know better, we'll let you know how it's going to be done. That includes the midterms that we had to cancel. Maybe we'll have to cancel it completely, even though I try to come up with some other way of doing it. And the homework. The homework, though, is going to be pretty straightforward. You just send your complete homework to me by email when I announce it, and you'll get your grades back in the grade book. And we're still considering what to do about getting your work back to you. Perhaps we'll organize a chat with a grader so that he can answer your questions about the grading. So at this point, this is what I have to say. Now let's see. Let's try a test question, but I don't want to be flooded by questions. So maybe someone can ask a question, and I'll get it in 10 seconds. No, okay, all right. So it doesn't seem to work, right? Okay, all right. Then we just start the lecture. All right. So again, this is the first time, so nothing is supposed to run smoothly. All right, so it's been a large break that we had, the spring break, and
what is 1 to the power of 0?
That's the question. What is it? What's the answer? All right, it's 1. I got it. All right, so the previous time we stopped our discussion at the chemical potential and the Gibbs free energy. And the last example, the last equation that we wrote down, that was the absolutely last equation that we had, was that the Gibbs potential of a system was equal to the number of particles in the system times the chemical potential. And we had some discussion on what it means. It means that the chemical potential is just the Gibbs free energy of a system per number of particles, or if you like, this is by the chemical potential is by how much the Gibbs free energy of the system changes as you add one particle to the system. All right. So and I guess no, that was not the last equation that we wrote. We said that for a system containing more than one type of particles, the Gibbs free energy was given by the sum over all particle numbers of the appropriate Gibbs potentials, right? And this is where we stopped by noting that the chemical potential of the mixtures are not necessarily equal to the chemical potentials of the actual substances. All right. So now there was one thing that that I didn't have time to do, and give some example on this, on application of this equation. And the example that I would like to give is the chemical potential of the ideal gas. All right, so here is an example. Chemical potential of ideal gas. Chemical potential of ideal gas. Now, so mu, the chemical potential, is G over N. D mu dP at constant N and T is from the appropriate thermodynamic identity 1 over N dG dP at fixed N and T, right? And now, if I go back and look for the thermodynamic identity for G, I can see that the GDP at fixed N and T is equal to the volume. Therefore, it is equal to V over N, which for the ideal gas is KT over P. All right, KT over P. Okay, so this is the derivative of the chemical potential of the ideal gas at fixed N and T with respect to pressure. We used the fact that this is ideal gas at this point, where we used PV is NKT, right, for the ideal gas. This is how we arrived to this conclusion. All right, then, so I have the derivative at fixed N and T. I can integrate it at constant N and T. Therefore, at T n constant, this derivative becomes a regular derivative, and I can take the appropriate integral. Mu then, let me write this temperature and pressure minus mu temperature sum 0 pressure is equal to the integral from P naught to P of KT over P, right? And then I can take this integral, and what I obtain is that the chemical potential as a function of temperature and pressure is given by the chemical potential at the same temperature and different pressure plus KT log P over P naught. All right. So what I did, I used the thermodynamic identity and the fact that mu is G over N to determine the dependence of the chemical potential of the ideal gas on pressure. All right. So perhaps it's not much, but if we are working with a fixed amount of gas at constant temperature and change the pressure, we know how the chemical potential changes. All right. Now, since the ideal gases do not interact, this equation also works for mixtures of the gases, and well, it's one useful equation. Now, again, this is something that I wanted to do at the last lecture. I didn't have time to do it, so maybe a little bit out of tune today, but I wanted to give an example on how the equation for the chemical potential that we obtained can be used on the example of the ideal gas. All right, and then again, you see that all those things are just some play on with the thermodynamic identity and taking partial derivatives. It's actually not difficult to do, and we'll get homework problems on this subject, but you need to just get used to it and try to do some exercises. Therefore, the homework problems that we give actually drive you step by step with what you need to do. In any case, all right, so this kind of finishes our previous topic on the thermodynamic identity and the free energies, Gibbs free energy and Helmholtz free energy, and some stuff on the chemical potential. All right, now we are ready to move to a new topic now, and this topic is phase transformations. Actually the equations that we've got and the concepts that we developed, those of thermodynamic identities and thermodynamic potentials, are very much applicable to the phase transitions, and that's why we are doing them after we learn about these thermodynamic potentials. So phase transitions can occur in systems containing one substance or in systems containing many substances, obviously. We start with the one substance phase transitions. All right. So the simplest example is, of course, boiling water. I have water in a liquid state. I change the temperature. Water becomes vapor. Now, it's the same substance, H2O. However, now it's in a different form. It's in the form of gas instead of a form of liquid. This is an example of a phase transition. And a phase transition in general is, well, it's a change of a phase of a system, but how you define a phase, we'll learn from examples. These are different states of the same material. Obviously, when you change something from liquid to gas, or from liquid to solid, or you can actually go directly from solid to gas, it is obvious that the state of the substance changes and that you are dealing with different phases. And then we're studying phase transitions. You can talk about different kinds of phases. For example, the substance can be magnetic or non-magnetic, and you can get a transition from, yes? Those two? Or those two? I see. Okay. All right, no problem. So I guess I'll use those two. All right. So you are on those two now, right? Okay, that's fine. Yes. So I'll use those two. All right. Yes. Again, so the substance could be magnetized and non-magnetized, and there could be a transition from non-magnetic state to a magnetic state. That's a different example of a phase transition. Or various other things can happen. Phase transitions can occur as functions of temperature. Again, the obvious example is boiling water. Or as you change some other parameter. For example, you can change the pressure in the system, or you can apply, I don't know, a magnetic field to the system, or do something else to it. All right? The important thing is that the state of the system changes from one recognizable form to another recognizable form. And then what happens, you get a phase transition. All right. So our next topic is phase transitions, more specifically phase transitions of pure substances. Phase transitions. Pure substances. Usually in thermodynamics we have more than one variable, temperature, but then what's the pressure, what's the volume, right? The minimum number of variables, as we keep discussing, is usually 3 in what we do, pressure, temperature, volume. Therefore, we are dealing with problems in many dimensions. We're dealing with problems in many dimensions. So there is a good way of visualizing what happens at the phase transitions. This good way is called plotting a phase diagram, right? So we have several variables. Let's say we have 3, right? Then only two of them are independent variables, because there is usually, or there is always some kind of an equation of state relating the variables together. Therefore, only two of them are independent. And so in this simple case, I can plot things in 2 dimensions. All right. So, for example, I can make what is called a phase diagram. Let me put the 2 different axes: pressure on the vertical axis, temperature on the horizontal axis. And what I'm going to plot actually is the phase diagram of carbon dioxide, CO2. All right. This is 0. 0 pressure, 0 temperature in degrees Kelvin. And, you know, I know that at high temperatures, I get gas. I know that at low temperatures, I get solid. I also know that at some intermediate temperatures and pressures, I should get liquid. At this stage, we just need to do the experiment and see what we get. And turns out that for CO2, the phase diagram looks like this. This is liquid. So, if I choose a point in this phase diagram, that is, if I'm at a certain pressure and certain temperature, and through the equation of state, I can get the volume. So there is a third variable lurking here, but I know it once I know the 2 variables. All right? So let's say I'm here at this temperature and this pressure. I know that I get gas. If I'm staying at the fixed pressure, and for example, change the temperature, I'm cooling the system down, you see that at this particular pressure, I go directly from gas to solid. Or if I start here, and I cool the system at fixed pressure, I go from gas to liquid, then to solid. All right. Now, there are a couple of special points in this phase diagram, and I'll just briefly tell you what they are. There is a special point here, which is called the triple point. It is called the triple point because at this particular combination of temperature and pressure, all the 3 phases of carbon dioxide can coexist, right? So at this point, you can get solid, gas, liquid coexisting, right? There is another special point in this diagram. It's called the critical point. So this is a triple point. Triple point. This is a critical point. And if you think about it, then the existence of the so-called critical point is a very curious fact. Let's suppose that I start here in a solid phase, right? And I change whatever parameter I would like to change. In order to get from solid to liquid or to gas, I must cross the so-called phase transition boundary. I must cross one of those lines over here, or maybe 2, to get to some other point. And therefore, I must go through a phase transition. However, if I start in the gas phase, right, I don't have to cross the phase transition boundary in order to get to the liquid phase. I may do so. For example, I can start here, start increasing pressures, then I go from gas to liquid through a phase transition boundary. However, I can also start here and go a different route and also end up in the liquid phase. All right? I can go around the critical point. What it means is that the properties of the system will change in some kind of continuous way, and I can continuously go from gas to liquid without crossing any phase transition line. What it tells us that the gas and liquid phases have some similarity to each other. some common property, while the solid phase is quite different. I cannot go from solid to liquid or to gas without going through phase transition, but I can go from the liquid phase to the gas phase without undergoing any kind of a phase transition. So these are curious facts. They are related to the symmetry of the system. Solid has a long-range order, has a certain set of symmetries in it, while gas and liquid don't. All right? I'm not going to dwell on it. I just want to state the facts now. All right? So what can you get for a phase transition? Okay, so the important thing to learn from what I was saying now is that substances, pure substances, can exist in different phases, right? You can go from one phase to another by changing the external parameters such as temperature or pressure or both of them. And in the process, you can go through phase transition, or you don't have to under certain circumstances. All right? Okay. Now, of course, this is just one example of a phase diagram. There are many other examples, and perhaps the simplest one can be plotted using temperature and magnetic field axis. And this is type 1 superconductor, the so-called type 1 superconductor, which has a superconducting phase and the normal phase. Normal phase. Normal phase. All right? This is so-called TC, the transition temperature at zero field. So at high temperatures, the material, the superconductor, is in the normal state. It's not superconducting, it's just a regular metal. As you cool it down at zero field, it becomes superconducting at certain temperature, which is called TC. If you apply the magnetic field, the material ceases to be superconducting and becomes normal. That's another example of a phase diagram. And there are many, many, many more examples. In fact, if we started talking about the magnets, the phase diagrams don't even have to contain some kind of extended two-dimensional regions. The phases can be confined to points or lines. The last example I am giving is this. Temperature, magnetic field again, and I'm talking about the ferromagnet. Ferromagnet, which is a material that can have a magnetization. At zero field, there is a certain temperature. We'll again call it TC. And before that, below that, the material will have a state with zero net magnetization, but however, it will have magnetic domains along these lines, while at any applied field, it will have a finite magnetization. All right? So you can get something that is confined to a line or a point. Now, for us, we need to come up with tools of dealing with phase transitions. We'll get some very useful ones, all right? But before we go to a useful one, or really useful one, let me give you a couple of examples that illustrate what you can do using just the basic thermodynamic identities that we have obtained. Now, the important thing we need to remember is that phase transitions occur in interacting substances, in substances with some interaction between the particles. No phase transition occurs in an ideal gas. The ideal gas remains ideal gas under any condition, right? Therefore, in order to get a phase transition between the phases, you need interaction between particles in the system. All right, so now, the key question is which phase is realized at a certain temperature or pressure? The answer is that we already know that the equilibrium state of a system at fixed pressure and temperature is characterized by the minimum in the Gibbs free energy. All right? Okay. So, if by some magic I can calculate Gibbs free energy for, let's say, gas state and liquid state of a given substance, then I can tell that whatever phase has a smaller Gibbs energy will be actually realized in thermodynamic equilibrium. All right? So that's a pretty general statement, but this is all we can say. So the question which phase is realized, realized at given temperature and pressure, the one that minimizes G is realized. All right, so as we know, as we already mentioned many times, for real substances we cannot really calculate thermodynamic potentials. However, we can measure them. And there are really well-defined ways of measuring all those things. Remember, the internal energy, the enthalpy, the entropy, for each of those thermodynamic quantities, we had a way of experimentally measuring them, right? So in principle, we can take one substance and measure all those quantities. All right, so example. Solid carbon can actually occur in many different states and many different phases, but the two most common states in which solid carbon exists is diamond and graphite. Diamond and graphite. All right, so we know that actually at normal conditions, atmospheric pressure and room temperature, graphite is a more stable phase. All right? So we know that, and we can measure by, but we also know that diamonds do exist under normal conditions. What it means is that a diamond is not in thermodynamic equilibrium. All right? Meaning that if we wait forever, at some point it has to transform into graphite just by itself through some kind of thermal fluctuations. We also know that it doesn't happen in any reasonable time. This also happens in nature. So an unstable phase can be thermodynamically unstable, but can be separated from the stable phase by such a huge cost, or what we call the energy barrier, so that it never goes from one state to another. In any case, at temperature of 298 Kelvin and pressure of 1 atmosphere, G diamond minus G graphite is equal to 2.9 kJ per mole. All right, fine. So this is some kind of an experimental result. And now I'm going to do some magic with this result. I'm going to do some magic with this result. So somehow, using the measurements that we discussed at the previous lecture, we came to this conclusion that the Gibbs free energy of diamond is larger than the Gibbs free energy of graphite by 2.9 kilojoules per mole, meaning that under those conditions, once again, graphite is a thermodynamically stable phase. All right, so that's the fact. Now, if I go back to the thermodynamic identity for the Gibbs free energy, Actually, I can find it in my notes and write it down, because it's been a while since we did it. We know that dg is equal to negative s dt plus v dp plus mu dn, right? So this is the thermodynamic identity for G, all right? And now if I, just to remind you how it is done, if I fix T and N, what it means is that dt is equal to 0, dn is equal to 0, right? And I see that dg, I divide by dp, dp at fixed t and n is equal to v, right? So this is how I get all these partial derivatives from the appropriate thermodynamic identities. All right. Now, this is what I know for diamond, right? The difference in G. And then there is another fact which I can measure experimentally. And experimentally, of course, I can measure the density of diamond and the density of graphite, right? Meaning that for the same number of particles, fixed 10, I can see whose volume is bigger. The volume of a piece containing, I don't know, a million or billion or whatever, and Avogadro, 1 mole carbon in diamond, and for the volume for the same number of atoms in the graphite. Then I find that Vg is larger than Vd, meaning that graphite is less dense than diamond, all right, experimentally. Okay, so this is information I have. This is information I have. Now, what can I do with this information? Well, since I have the derivative dg dp, which is equal to v, right? I can say that I can plot g as a function of p for small change of p, right? So if I change p, the pressure, by a little bit, then the dependence of g on p will be linear. I'm using the first term in the Taylor series expansion. And I know this derivative. It is equal to v, right? Therefore, there will be two straight lines. And I know that the derivative for graphite will be larger than the derivative for diamond. Therefore, I can plot two lines here like this. All right. One is for the graphite. The other is for diamond. Now, which one is which? This is the room temperature and 1 atmospheric pressure. I know that there graphite has smaller. Therefore, this is graphite. This is diamond, right? Graphite has a steeper slope because its derivative with respect to p is bigger, right? So, I see that at some pressure, those lines should cross, and then the line that used to be below becomes above, and the line that used to be above is now below the other line. What it means is that at this pressure, diamond becomes thermodynamically more stable, and graphite becomes, the unstable phase. The graphite becomes unstable phase. Moreover, and what is important is that I know this difference, right? This difference is right here, 2.9 kilojoules per mole, right? This is 2.9 kiloj per mole. And I know both slopes because I can certainly measure the molar volumes of graphite and diamond at room temperature and atmospheric pressure. meaning I can get the position of this point. All right, meaning I can get the position of this point. Turns out that this is 15,000 atmospheres, or we will say 15 kilobar. Bar is 1 atmosphere. And so we see that from the experimental data that we have, we can conclude that if we apply pressure to graphite, if we apply enough pressure to graphite, it should convert to diamond. And moreover, from the data that we can measure, we can predict that this will happen at the pressure of the order of 15,000 atmospheres. All right? So that's a useful fact, actually. That's a useful fact. We also see why the diamonds form well underground. Turns out that 15 kilobars is about 50 kilometers in terms of rock depth, right? 50 kilometers in terms of rock depth. And, you know, of course, the temperature there is different. High temperature also helps. High temperature also helps. Anyway, this is a useful fact. This is a useful fact which we have derived from a very small amount of the data input, right? The molar volumes of graphite and diamond, and the difference in the Gibbs free energy at some kind of constant, at some kind of the initial conditions. All right, someone has the mic on. Please mute your mic. Yes, please mute your mic. Can you mute your mic, please? Okay. All right. So let me see. Is there a way? Is there a way I can mute this guy? Let me try. Please mute your microphone. Well, let's let me see what I can do. Alright, so can you please mute your microphone? All right. Okay. Looks like it's done. All right. Okay. So yeah, I'll need to figure out whether I can do it myself because it may become quite disruptive. All right. So this is useful stuff. Now, what I'm going to do now, I'm going to derive actually much more useful equation pertaining to phase transitions, which we'll be using for solutions of a number of practical problems. All right. So after all, measuring Gibbs free energies is a rather complicated stuff. Now, okay, it's back, right? Someone is back. All right, so what I'm going to do now, I'm going to unmute my yeah. How can I do this? Oh boy. Okay, I found how to mute someone. All right, forcefully. Okay, very good. All right, so looks like I can still rule this room, which anyway, sorry about this, guys. let's get to something more to something more useful. All right. So I'm going to derive an equation describing the so-called phase transition curve. The equation is called the Clausius-Clapeyron relation. I'm just going to write now the names of these guys. The Clausius-Clapeyron relation, and it allows us to calculate the phase boundaries between the two phases. So, this is what I'm talking about. Temperature, pressure, phase, I don't know, phase 1, phase 2, right? There is a line separating these two phases. Let's suppose that this is, I don't know, ice and water, right? The line separating ice and water doesn't look like this, but let's suppose this is ice and water. I know that under normal pressure, water freezes at 0 degrees centigrade. I would like to figure out what happens at different pressures. Okay? Now, I can simply do the measurement, or, in fact, if I don't have the capability of applying the pressure, I can do something else. This something else is allowed by the derivation that we are going to do. All right, so now, phase 1. Here, the Gibbs free energy of phase 1 is smaller than that of phase 2. Phase 2. Here, phase 2 is stable. The Gibbs free energy of phase 2 is smaller than the Gibbs free energy of phase 1. What happens at the phase transition line? This is where Gibbs free energy of one phase is equal to the Gibbs free energy of the other phase. All right? Therefore, here, G1 is equal to G2. All right? Okay. So, I can certainly differentiate what I have here and write that dG1 is equal to dG2. Then I can take the thermodynamic identity that we have already used today, that I had written on the blackboard before. dG1 is equal to dG2 means that negative S1 dt plus V1 dP is equal to negative S2 dt plus V2 dP. Now, this is the same material, and therefore the number of particles doesn't change. All right? Therefore, I can get rid of dN in the thermodynamic identity. S1 is the entropy of phase 1, could be molar entropy, for example. V1 is the volume of phase 1. S2 and V2 are the entropy and the volume of phase 2. Okay? All right, very well. And I can solve, and of course, P and T are just the variables, they are identical. I can solve this equation for dP dt, and this is what I get. I get dP dt by solving this equation is equal to S1 minus S2 over V1 minus V2. Okay, that sounds pretty easy. Now, in this equation, you see that you get non-zero dP dt. That is, and what is dP dt here, right? dP dt is calculated assuming that G1 is equal to G2, right? So this is the condition under which we wrote down the equation for dP dt. Meaning that this is dP dt for the phase transition line. All right? So what it tells me then is by how much the transition point changes as I change something. So if I change temperature, then the phase transition will occur at a different pressure, and dP can be calculated from this equation. Alternatively, if I change pressure, the phase transition will occur at a different temperature, and this dt can be calculated again from the equation over here. Or, in other words, it gives me the slope of the phase transition line at a given point. All right, dP dt. So this is the slope of the phase transition line. This is the slope of the phase transition line. All right, now, measuring these is usually not difficult. So I can have water, I can have ice at zero centigrade temperature. I can certainly measure what happens when the water freezes and by how much the volume changes. All right? Now, what about entropy? What about the entropy? Well, for the entropy, we have a very useful equation. For the entropy, we have a very useful equation from the thermodynamic identity. We know that if the process is done slowly enough, that is, it is quasi-static, the change in entropy is equal to the heat divided by the temperature. All right? So, slow process, delta S is equal to Q over T, right? Is equal to Q over T. So as I go from one phase into another, right? And of course, I do it at a fixed temperature. So let's talk about ice. This is 0 degrees centigrade. I go from water to ice. There is some heat, either absorbed or released. We have a name for this heat. For this heat. This heat is called the latent heat of the phase transition. All right? Remember, we discussed it before. If you are, I don't know, boiling water, right? Your water is at 100 degrees centigrade. In order to make it all vapor, you need to apply additional energy. This additional energy is called the latent heat of vaporization. If you are melting ice, ice is already at 0 degrees Celsius. In order to make it water at 0 degrees Celsius, you need to provide energy. This energy is called the latent heat of melting ice. If you go through a reverse process, for example, you are condensing vapor and make it water, you need to take the heat out of the system. That's the same heat as the heat of vaporization, but taken with a different sign. Instead of putting the heat energy into the system, you are taking it away from the system. So this is called the latent heat, right? And therefore, for the phase transition, this is simply L over T, where L is the latent heat. All right, then, I can go back to this equation and replace S1 minus S2, which is delta S, which is by how much the entropy of the system differs as I go from one phase to another, by L over T. And therefore, then, I obtain the following equation. That's our final equation. Which goes as follows. dP dt is equal to L T over delta V. This is the Clapeyron-Clausius relation. And it applies to, I don't know, liquid gas, solid liquid, or other types of transitions where you have the latent heat. Now, when the equation is written in this form, there is one confusing part about it, namely the sign. All right? So the latent heat we can get from the table, of course, heat of vaporization of water, for example, but whether you put it here with a plus or minus. This question causes a lot of confusion, and in order to make the situation, completely transparent, one simply needs to go back to the original equation. That's why I wrote it for the first, but I won't actually write it back. I didn't want to erase it, but I only have 2 panels here. So, okay, dp dt is still S1 minus S2 over V1 minus V2, right? This equation doesn't have any ambiguity about the sign. This equation doesn't have any ambiguity about the sign because let's say we are talking about water, liquid water, and vapor, right? Then dp dt is equal to S liquid minus S gas over V liquid minus V gas, right? And then there is no ambiguity here, right? Volume of the liquid, let's say per mole, volume of the gas, and then this is the entropy of the liquid, this is the entropy of the gas, right? Of course, the high temperature state has larger entropy, so you know which sign to use. All right. So once again, technically this is more useful, but there could be some confusion about the sign in this equation. You can get the sign by going back to the original equation. And you always know whose volume is bigger, the volume of which phase is bigger, and you always know the entropy of which phase is bigger. This is a high temperature phase. All right. Okay, so now this is a useful equation, and one example of its application, which you'll have in your homework, is what happens to the phase transition temperature of liquid water into ice when you apply pressure. Turns out that when you apply the pressure, the melting transition of water goes up, and therefore, if you apply enough pressure, ice becomes water. Ice becomes liquid water. All right. This is sometimes used for the explanation of why sharp skates slide so easily. I don't think it's right, but this is sometimes what is used as an explanation. All right. Okay. So this is a useful equation. We know what happens to the phase transition temperature. As you change the pressure, you know what happens to the phase transition pressure as you change the temperature. The very unsatisfactory thing about everything that I said by now is that everything so far depended very much on the experimental data. So I needed to get some numbers for free energies or entropies or whatever, some other thermodynamic potentials from experiments. And, what we have here is not nothing, in a sense that if we do, let's say, measurements at one temperature and pressure, we should know what happens at different set of conditions. But nevertheless, in physics, it is always useful to come up with some kind of a model and study its properties. The enormously important model in thermodynamics is that of the ideal gas. It's useful. There is an equation of state describing the state of the ideal gas. We can do a lot of it. However, ideal gas has no interaction, therefore it doesn't exhibit any phase transitions. we have studied other models. Remember the, let's recall the, what did you do, the Einstein solid. We did the two-state paramagnet, right? And for those models, we have calculated the thermodynamic properties, various thermodynamic properties, and that was quite satisfactory. Moreover, for some of these systems, such as a two-state paramagnet, there are actual experimental realizations in nature, and then it becomes even more satisfactory because you can come up with a microscopic model describing the behavior of a system on the macroscopic level. So it would be nice to have something for phase transitions. Then the problem is, as I said, you need to introduce interaction into the system. And once you introduce interaction into the system, things become enormously complicated. All right, things become enormously complicated, but we can still do it with some degree of success. And in any case, we will learn a lot even from simple models, even if they are not describing our specific bottle of water that we cool down, freezes, the bottle explodes. We would like to know why. It's actually very difficult to answer this question from the first principles. But we can do something that still shows properties of phase transitions and what you can expect in the real-life systems. And our next step is one of such models in which you have interaction and in which you have a phase transition. And this is a famous model which actually applies to real-life gases, and it's called the van der Waals model of gas. This is our next topic, the van der Waals model. So again, ideal gas doesn't exhibit any phase transition. Moreover, remember that when we talked about refrigerators, I plotted a cycle for a real-life refrigerator. We found out that real-life refrigerators include a non-reversible process, the so-called Joule-Thomson process of expanding gas, and this is where most of the cooling occurs in a real-life refrigerator. We found out that for the ideal gas, this effect of cooling is equal to 0, and therefore the ideal gas model certainly doesn't work for real-life refrigerators. And again, if you apply pressure to the ideal gas, it never becomes a liquid. In this model, in which we have some model for the interaction between the particles and which is still solvable, both of these things are fixed. You get a phase transition, and you can get some kind of cooling for real-life refrigeration. So this model is actually quite famous. This was perhaps the first model with interaction that was introduced in thermodynamics, and which works for real-life gases, at least in some primary range. All right. So we need the equation of state. In order to get the equation of state, we need to introduce interaction between particles. Interaction between the particles of the system. This is how we are going to introduce it. Firstly, we will give particles a size, all right? Meaning that when we fill the volume with particles, the actual volume available for the other particles becomes smaller. This is easy to understand, all right? So we're throwing billiard balls into some vessel. At some point, the balls will fill the vessel. There will be no volume for the balls to move. All right. Therefore, and of course the volume that we exclude is directly proportional to the number of particles. Therefore, the first thing we are going to do is very obvious. We'll replace V with V minus NB. N is the number of particles, B is a constant, N times B is the excluded volume. Excluded volume. So we exclude it when we fill the system with particles of finite size. Now, in reality, what we do here, we are introducing repulsive interaction between particles. All right? So you can think about repulsive interaction, which is very weak at small distances and becomes very, very strong at short distances. And you can give it some, specific boundary distance at which the interaction becomes strong. So this is taking care of repulsive interaction between the particles when they get too close together. All right, now, this is repulsive. This is effective repulsive interaction. A repulsive interaction. The particles repel, if the particles repel each other, just repel each other, nothing interesting happens actually. They'll stay away from each other and you still get some kind of a gas phase. Therefore, we also need to introduce attractive interaction into the system. And this is a bit more tricky. So, attractive interaction. Attraction. Let me plot my molecules. And let me fix the molecules. Let me fix them. Fix the molecules, all right? Now, the number of neighbors for a given molecule is simply proportional to the density of the stuff, okay? All right. So I fix a molecule. It will have neighbors, let's say nearest neighbors. The number of neighbors is proportional to the density, that is N over V. All right? Now, if I fix the molecules, as I have shown here, there will be some typical distance between the molecules. And for this typical distance between the molecules, there will be some kind of typical attractive interaction. All right? Now, I'm talking for one molecule here, for one fixed molecule. This typical attractive interaction, I can designate it by some letter, which will depend on the substance, A. So, for a given molecule, the interaction is given by minus A over N times N over V. So once again, this is what I'm doing. This is the interaction for a given molecule. It has some typical value A for a molecule interacting with another molecule. And the number of neighbors is proportional to N over V. Therefore, for a given molecule, this is what you get. And I put everything into this little constant A. All right. This is one molecule. There is N molecules. Therefore, for the entire system, N molecules, the interaction is constant, negative constant A times N squared over V. I just multiplied minus A times N over V by N. Now, the origin of the negative sign here is, of course, because the interaction is attractive. Remember the potential, recall the potential energy for the gravitational objects. It's minus g times m1 m2 over r square, over r, sorry. Recall the Coulomb energy of interacting charges. If the charges attract, then again there is a negative sign in front of it, right? So the negative sign here simply indicates the attractive nature of the interaction. Okay. All right, so we have excluded volume, and we have the interaction in the system, attractive interaction in the system, which is given by negative a some constant, times n square over v. All right. Okay. Yeah. Now, there is one additional non-trivial step that we need to make before we can write down the equation of state. All right, so when we introduce the attractive potential, I fixed the molecules in place. And then it was kind of natural to get the equation minus a times n squared over v. All right. But what did I do when I fixed the molecules? I neglected their thermal motion at this point. Therefore, it means that I turned off T and I turned off the entropy. So, molecules fixed in place, means that I neglected T, thermal motion, and S. So if I am consistent, I can write that then du is equal to minus p dv for the thermodynamic identity, or p is minus du dv, okay, fine, at fixed S. Okay, so this is the equation, and therefore this pressure change, or rather this pressure due to the interaction that we introduced in the system is given by this equation. So let me write the equation first and then explain what I mean. So pressure due to attractive interaction I'll write the equation, then I'll tell you what it is equal to minus d dv of negative a n square over v, which is of course negative a n square over v square. Here is the equation, now the explanation. So in the equation of the ideal gas, the origin of the pressure is in the thermal motion of the molecules. Molecules are moving with some whatever different velocities, let's say with some typical velocity. They hit the walls of the container, they apply pressure. The origin of the pressure in the ideal gas is fully kinetic due to the motion of the particles. All right? Now, I'm saying that I'm introducing some kind of attractive interaction between the molecules. What is it going to do? It's attraction. Attraction between molecules. It's going to reduce the pressure in the system. The question is by how much? In order to determine by how much, I fix the molecules in place. I neglect their thermal motion. I only care about the attractive interaction between those molecules, I know that the energy of this interaction is negative AN squared over V. Okay? And then from the thermodynamic identity, I get the pressure coming out of this energy U. I differentiate with respect to E, put the negative sign in front of it, and I get the negative pressure that I expect. But the meaning of this negative pressure is that it gives me the change of the pressure in the system when I introduce the attractive interaction. This is a little bit convoluted. This is a difficult argument. But this is how I built my model. You know, we'll be done soon, so bear with me for next few minutes. What it means is that we determine the change of the pressure within the framework of our model, that the pressure now becomes the original pressure of the ideal gas due to the kinetic effect, plus this pressure due to attractive interaction. All right. Pressure due to attractive interaction. So this is this pressure minus AN square over V square, right? And this original pressure P comes from the equation of the ideal gas, NKT V minus NB. We already replaced V with NB. Now, I could, in principle, put V minus NB under the square here, but that introduces a small effect because this is V square and the change is small. So I keep it at V. And now let me collect two things together. V is replaced with V minus NB. P is replaced with P, given here, minus AN square over V square. All right? And now I collect everything together, and we'll be done. Now I use the equation for the ideal gas with modified pressure and volume. This is what I get then. P plus A N square over V square times V minus NB is equal to NKT. Okay. All right. So this is a so-called van der Waals equation. Depends on two parameters, and now we need to analyze whether this equation provides us with anything useful. This is a modification of the ideal gas law with some kind of system-dependent parameters A and B. This is the subject of the next lecture. But now let me, in the end of the lecture, say a few announcements. So again, the situation may be changing quickly. The format of these lectures may change quickly too. We'll keep you informed about this. We'll try to fix the problems that we had today. Today is our... Say it again. He can't hear me? Right. Okay. So, yeah, let me try it. So now I unmuted myself on the WebEx, and you guys can probably hear me on the WebEx, right? They should be able to.
Yeah, how do we define B constant?
Uh-huh.
Yeah, we never define.
Right.
Just never explained it.
Right. The question is how we define the B and A constant, actually. The answer is you take them from experiment, but I will say more about this at the next lecture, because in the next lecture we are going to analyze the van der Waals equation in more detail. Now, V minus NB, yeah.
Should have n minus nb.
Oh, 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 oh. Good. All right. Sorry about this. This is V minus NB. Yes, of course. Yeah. All right. So yeah. Okay. So we will try to fix several problems when we meet next time. But a few things. So firstly, keep checking your email because I'll send you all the changes by email. Secondly, I'm going to assign homework very soon today, right? You'll still have 1 week to do it and submit it by email. The details will be in my email. I will also post them on the course website, so hopefully that will work. So for now, I'm switching to WebEx, and I can answer questions on WebEx in real time. Okay? So if you go back to WebEx, and we can chat for a while now. I'm stopping the broadcast. All right. So I understand that